Hello and welcome back to Manifolds, the video series where we talk a lot about differential forms, Riemannian metrics and so on. And in today's part 37, I want to talk about a very important vector field for submanifolds. This is often called the normal vector field. However, in order to be precise, we should say that today we talk about the continuous unit normal vector field we can have on a Riemannian manifold. But as always, before we start, I really want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Using the membership option on Steady or here on YouTube is the easiest option for me and you to support me. And of course, as a member, you can get access to the additional material for all the videos. Okay, then I would say, let's immediately start with a nice picture of a two-dimensional submanifold. So you could say this is just a surface embedded in R3. And therefore, it's definitely also a Riemannian manifold. It just inherits the standard Riemannian metric from R3. More precisely, what we want to have here is an orientable Riemannian manifold of dimension 2 embedded in R3. Because then we have a nice visualization for the tangent space at a given point as a plane. Moreover, if we have a parameterization, we also get the two tangent vectors that span this tangent space. And now, since everything here lives in R3, we can take the cross product to find a normal vector for the tangent space. And there, as an interesting fact, you might already know that the length of this normal vector gives us the canonical volume form of M. Indeed, in the last video I have shown you an explicit calculation for graph surfaces. However, the relation is completely general simply because the length of n is related to an area. And this fits because we have a two-dimensional volume form here, which means we want to calculate areas on M. But now it turns out that we don't have to stop at dimension 2, we can define such a normal vector for a lot of submanifolds. Hence, in the next definition, we consider submanifolds in Riemannian manifolds. So let's call the surrounding Riemannian manifold M tilde. And inside M tilde, we find our submanifold M. And of course, a natural case would be that M tilde is just Rn. But this does not have to be the case. M tilde could be, for example, just this sphere. And then we could visualize M as a submanifold here. And then in the picture, you should recognize that we could also have normal vectors here. At each point, it should be tangent to the sphere, but normal to M. So putting this at each point, it would look like this. And this is exactly what we want to define now, a map capital N. And the input is a point of M, and the output should be a tangent vector. However, it should be a tangent vector of M tilde. So more precisely, we should say we take a point P from M and the output N of P is an element in Tp M tilde. However, we also want more. We also want the orthogonality here. So we also want that the output is orthogonal to the tangent space of M. So we simply say we have the orthogonal complement. But of course, there we have to exclude the zero vector as well. Obviously, the zero vector is always orthogonal to every vector, therefore not so interesting. Okay, and now with these two ingredients here, we have a map that we call a normal vector field. And there you should see, normal makes only sense if we have a surrounding manifold M tilde. Because then we can see the tangent space Tpm as a subspace in Tpm tilde. And this is quite important, because otherwise we could not work with the orthogonal complement here. Moreover, please don't forget, orthogonality here is seen with respect to the Riemannian metric Gp. In other words, we have a well-defined inner product on both vector spaces. Of course, everything here is much simpler if M tilde is just Rn with the standard inner product. Because then we also have the simpler tangent space for submanifolds. Therefore, I would say, first think of the case of submanifolds in Rn. And then it might be clear that we also want a little bit more. We want a continuous normal vector field. This means if we change the point in M a little bit, we also want that the normal vector only changes a little bit. It should not completely flip around, and then we would say it's continuous at the point P. And usually how we do it in a definition is that we just go to charts of the manifold. So we just take a chart UH of the big manifold M tilde, and then as always we get a coordinate basis of the tangent space. And as you already know, we have a common name for that, we call them del IH. So for each point x in the open set U, they form a basis of the corresponding tangent space. Hence, every tangent vector can simply span with this basis. So we can simply take coefficients AI and form a linear combination. And that's it. This is how we can write n of x as well. And of course P should be in the chart, which means now we can wobble around this P a little bit. And then the normal vector will not change a lot if these coefficients AI are continuous functions. So indeed, continuous functions from U to R. And then you might know, the common extension of this definition is to say that n is continuous if it's continuous at every point P. However, we want to extend it more because we also want to talk about a unit normal vector field. So this is a really long word. We want to have a continuous unit normal vector field. And there you see we want to have two properties in addition. First, it should be continuous and it should be unit in some sense. Now, the first thing is easy to write down. So we want to be continuous at every point P in M. And now the second point is that the length of n is exactly 1. Obviously, we could just denote the length of n with the norm symbol, but then the question remains, which norm do we take here? And of course, since we work in a Riemannian manifold, there's only one sensible choice. It should be the square root of the inner product given as gx. So into the Riemannian metric, we put the two vectors nx and nx. And of course, taking the square root gives us a length. And this now should be equal to 1. And this should hold for every point, so in our case for every x in M. If we write x or p, it does not matter here. Okay, so this is the definition of a continuous unit normal vector field. And now you might ask, why is that useful at all? We already mentioned some connection to the canonical volume form, but it turns out that such a vector field here is related to the notion orientable. So please recall that the definition of an orientable manifold was somehow complicated but also very important. And I have to say, making a connection to this unit normal vector field makes this definition really easy to visualize. Therefore, now I want to tell you this important fact we have for submanifolds. More precisely, we want to consider submanifolds of codimension 1. This means there should be embedded in Rn and there should be of dimension n-1. And please never forget, this is a Riemannian manifold because Rn just carries the standard metric. Okay, so now the typical example you can have in mind here would be the two-dimensional sphere in R3. And now it turns out, for such manifolds, we can rewrite the notion orientable. Because we have that M as a smooth manifold is orientable if and only if we can find a continuous unit normal vector field on M. And indeed, this equivalence is not hard to prove if you already know the notion orientable well enough. So maybe check out part 32 again and try to write down a proof for this. However, this equivalence is the reason that sometimes the existence of a continuous unit normal vector field is used as the definition for the notion orientable for submanifolds. In fact, it gives a very nice visualization because it means if you can have normal vectors everywhere, we have an orientable manifold. And you see this is not possible for the Möbius strip because if you start with some normal vectors, at some point you have to flip them completely. So you cannot satisfy the continuous part here simply because the Möbius strip only has one side. And that's exactly what we have on the Möbius strip, an orientation in a continuous way on the Möbius strip is not possible. So please remember this important connection. If we are orientable, we also have a continuous unit normal vector field. Moreover, we also already know that being orientable is connected to having a canonical volume form. And there you see it. This is where we have the normal vector field connected to the volume forms. So if n is a continuous unit normal vector field on M, we have a very nice formula for the canonical volume form on M. And as usual, we denote it by omega m. And this nice formula reads that n can be combined with the volume form on Rn. And of course, the volume form on Rn is simply the determinant. Now a common symbol for this is this one, which simply means that we put n into the determinant. So here we transform an n form into an n-1 form. In fact, it's not a complicated notion at all, because it simply means that at the point x, this volume form gets n-1 vectors. So let's simply call them v1 to vn-1. And then we simply use the n form, which is given as the determinant here, to calculate the result. And then we simply put in nx as the first input, as the first vector, and then the other vectors as well. So not complicated at all, we just substitute the one missing vector with n of x. And as always, we see the tangent space for submanifolds as subsets in Rn. So indeed, this identification is the one we always have. Okay, so now this formula is really interesting because it means we can calculate our volume form on the manifold by using the higher dimensional volume form. And in fact, this is not so hard to visualize. Just imagine a two-dimensional manifold in R3. And now the volume form on M is about calculating areas on M. And now we can use the normal vector here, which has length 1, to transform this area into a three-dimensional volume. And now this volume here lives in R3 and can be calculated just in R3. So you could say the three-dimensional volume is the height times the area. However, since the height is given by the normal vector with length 1, we know that the volume is equal to the area. This is already the whole idea, it makes sense, and it gives us this nice formula here. However, if you want to prove it in general, you just have to put in a positively orientated basis of the tangent space. It's not so complicated, therefore maybe something we should discuss in the comments. Here, for the end of this video, I just want to show you an example. Namely, as I already told you, we can look at S2 embedded in R3. So we have the common two-dimensional sphere, and it's not hard to see how to put in the normal vectors there. In fact, we can just say n of x is given as x. The three-dimensional vector x that describes a point on the sphere can be also chosen as the normal vector. This is easy to visualize, it points directly into the correct direction. And most importantly, it has length 1. And now we know in general, this determinant or the square root of this determinant is the important ingredient of the canonical volume form. And if we take our standard parameterization with spherical coordinates, we already know how to calculate that. Namely, we just have to put in the coordinate basis with respect to this parameterization. And now we know that we can calculate this whole thing just by using the determinant in R3. The first input we have is n of x and then the two tangent vectors. And that's it, that's all we have to do. Now just calculate the determinant here. If you really write it down with all the inputs, it does not look so easy, so maybe let's do it. Now the first column is just n of x, so just x, or with the parameterization, this vector here. And then comes the first partial derivative, which means with respect to theta. Hence, we get this nice column here. And then finally, the third column is given as the partial derivative with respect to phi. And there we have it. This is the real nice 3 times 3 matrix. And now you can calculate the determinant. And what we see is that we get out sine of theta. So you see, by having a normal vector, we have an alternative way to calculate this Kramian determinant. And in fact, this determinant formula finally explains why the cross product of the two tangent vectors gives us the quasi-determinant as well. Indeed, in R3, the cross product will give us a normal vector, but not normalized. So you see, we have a lot of connections, but they all lead to the canonical volume form. And with that, I think we are ready to start with integration on manifolds. So I really hope we meet in the next video, and have a nice day. Bye bye.